Good afternoon. I'm Spot On Weather meteorologist Matthew Euler, and today we're starting the 2021 video summer training series on various weather topics, so I certainly hope you enjoy this presentation. We're going to start off and talk today about seasons and radiation. For example, what causes the seasons and the very important role that the incoming solar radiation plays, as well as outgoing long-wave Earth radiation plays into our temperatures throughout the course of the year. This graphic here shows the Earth in relation to the Sun. To start off the title slide of today's video, and that little globe over on the right, that is the moon in this picture. So let's go ahead and get to the important topic of seasons and radiation. We'll first start this training video off with a little bit of background information on the Sun. The Sun may be regarded as the only source of heat energy that is supplied to Earth's surface as well as the atmosphere. Now, all weather and the motions in the atmosphere are due to this energy radiated from the Sun. The Sun's core has a temperature of a blazing 15 million degrees Kelvin and a surface temperature of about 10,300 degrees Fahrenheit. So it's super hot, of course, the Sun. Now the Earth intercepts only a small fraction of this energy emitted by the Sun. Although it's very small, it's also very important as far as our temperatures. Looking at the overall solar composition, you'll see a graphic here on the left showing the different zones of the Sun. Starting out at the central core, where we have thermonuclear reactions taking place. And again, this is where temperatures can reach an astounding 15 million degree Kelvin. As we work outward away from the Sun, we work into what's known as the radiative zone, the convective zone, and then we get to the actual surface, the visible surface layer that's known as the photosphere, where the temperature is 6,000 degrees Kelvin. And working our way outward away from the core of the Sun, we get to the chromosphere as well as the corona. And so we'll break these down, starting off with the fact that the Sun, it may be described as a globe of gas heated to incandescence by thermonuclear reactions from within the central core itself. The layers, convective zone, this is going to extend very near to the Sun's surface, and this is where heated gases are raised buoyantly upwards with some cooling occurring and subsequent convective action. Now when I say convective action, think of in our own atmosphere thunderstorms. When the air gets really hot, the surface of the Earth heats up during a hot summer day, and because of that heating, that intense heating, you get rising air motion, and that results in clouds eventually as the air cools, as well as condensation when we change from a vapor to a liquid and form clouds themselves, and we get heavy enough droplets they will actually fall out of the cloud as rain. So convection is a heat transfer process where things extend basically in the vertical. It's a vertical heat transport mechanism. So the Sun being very hot in that convective zone, the temperatures being very hot, that's going to result in a buoyantly rising air upwards. Now the photosphere, this again is the well-defined visible surface layer of the Sun. The bottom of the photosphere is actually considered the solar surface. And all light and heat is radiated from the photosphere. So you definitely never want to do this. Never want to look directly into the Sun because you can actually sustain eye damage because of how bright the Sun is. But if you were to see the outline of the Sun, that really bright light portion of it, that would be the photosphere. And then working our way outward to the chromosphere. This is above the photosphere, and it exists, it is an area that exists that has more transparent gaseous layers. And it is actually hotter than the photosphere itself. And then finally, we go outward to the corona, which is a low-density, high-temperature region that is extended out to space by the solar wind. So some really interesting things here with the Sun. Moving on. Now that we kind of know what the sun does for us as far as weather goes, we're going to move on to the cause of the season, because the sun is still a consideration, something to take into account as far as seasons. Now, that revolution of the Earth around the sun itself and that tilt of the Earth on its axis are responsible for our seasons. So that's the two really main causes. The fact that the Earth revolves around the sun 365 and 1/4 days to complete one revolution around the sun, as well as that tilt of the Earth on its axis. That angle of the axis is 23.5 degrees to its plane of rotation, and basically we point in a nearly fixed direction in space toward Polaris, or the North Star. With the seasons, the diagram on the left kind of explains the tilt of the Earth. The sun is at the center of the diagram. You'll notice the Earth is on the outer ring here around the sun. And as we go from the different time periods throughout the year, I'll start by saying that the equinoxes, equinox literally means equal night, and then solstice literally means sun to stand. So we have two equinoxes and two solstices every year as the Earth makes this revolution around the sun. Important dates to keep in mind: March 21st, approximately that time, and September 22nd, approximately that date, is known as the equinox. The March 21st would be the spring equinox, and then the autumnal equinox would be September 22nd, right around there. Meanwhile, as June 21st, that one is known as the summer solstice, the first day of summer in the northern hemisphere, and then December 22nd is known as the winter solstice, the first day of winter in the northern hemisphere. So when Earth is in its summer solstice on 21 June, the northern hemisphere is inclined 23.5 degrees toward the sun. So the northern hemisphere is actually pointed. If you look at the graphic on the left, you'll notice the different numbers there: 66.5 degrees north, 23.5 degrees north. E stands for equator, and then 23.5 degrees south and 66.5 degrees south. The graphic on the left at June 21st, that shows you that the northern hemisphere, the North Pole, is actually tilted towards the sun. And this is the first day of summer in the northern hemisphere. You'll notice the southern hemisphere is pointed away from the sun on June 21st. So southern hemisphere locations, that's our first day of winter. As we move along now, when we talk about the sun's rays or angles of incidence, how direct are those solar rays? When we're talking about the summer solstice, more of the sun's rays reach the northern hemisphere as compared to the southern hemisphere. And direct sunlight on June 21st actually covers the area from the North Pole all the way down to latitude 66.5 degrees north, the Arctic Circle. The most perpendicular or direct rays of the sun on June 21st are going to be located over the Tropic of Cancer at 23.5 degrees north latitude. Now, during March and September, during the equinoxes, this is the time of year where the tilt of the Earth's axis is neither toward nor away from the sun. If you look at the diagram for March 21st and September 22nd, and you see the Earth in relation to the sun, the Earth is not pointed, neither of the hemispheres are pointed towards or away from the sun. So equinox literally means equal night. When we reach the equinox, Earth is going to receive equal amounts of the sun's energy in both the northern and southern hemispheres. And the most perpendicular rays of the sun at the equinox is going to be located over the equator. When we say equinox, literally the translation means equal night. Everywhere on Earth's surface has 12 hours a day and 12 hours a night during the equinox. Then we move along to December, around the 22nd of December. The southern hemisphere now is basically tilted or positioned towards the sun. So southern hemisphere cities are going to receive more of the sun's direct rays. And the most perpendicular rays overall of the sun are now going to be received at 23.5 degrees south latitude, or the Tropic of Capricorn. And the southern polar region is going to be in 24 hours of sunlight on December 21st, while the northern polar region is in darkness 24 hours. So this is the way, the seasons, this is how things happen. Again, the revolution of the Earth around the sun as well as the tilt of the Earth on its axis at 23.5 degrees. That is the cause of our seasons. Because of the way the Earth revolves around the sun, the incoming radiation received by the sun, it varies based on your latitude or your position on the Earth's surface. And because of this, we have what's known as Earth's natural light or heat zones. So because of its 23.5 degree tilt and its revolution around the sun, there are 5 natural light or heat zones. Now, since the sun is always going to be traveling between the Tropic of Cancer at 23.5 degrees north latitude and the Tropic of Capricorn at 23.5 degrees south latitude, this area between 23.5 north and 23.5 south is going to be known as the torrid zone or the tropics. Now, the zones between the Tropic of Cancer at 23.5 degrees north latitude and the Arctic Circle, 66.5 degrees north latitude, and between the Tropic of Capricorn in the southern hemisphere at 23.5 degrees south latitude and the Antarctic Circle, 66.5 degrees south latitude, this is known as the temperate zones. These zones receive sunshine all throughout the year, but less of it during the winter season and more of it during the summer season. And finally, the zones between the Arctic Circle, which is at 66.5 degrees north latitude, and the North Pole itself at 90 degrees north latitude, and between the Antarctic Circle at 66.5 degrees south latitude and the South Pole at 90 degrees south latitude, that area is going to receive the sun's rays only at specific times or parts of the year. And directly at the polar areas themselves, there are 6 months of darkness and 6 months of sunshine. So if you ever were to take a trip well up into the Arctic region, the polar areas, either the North or South Pole, you would notice that there's either 24 hours of daylight or 24 hours of darkness for 6 months of the year. It's really hard to imagine, being awake or trying to go to sleep, let's say, at 2 in the morning and it's still sunny outside. Just amazing. So those areas, by the way, are known as the frigid or the polar zones. Now, moving on to the radiation principles, and I really love this topic because this helps explain a lot of how temperature changes, not only on a daily basis, but also specific latitudes throughout the seasons. Radiation refers, first of all, to the process by which this electromagnetic energy is propagated through space, this EM energy. Now, electromagnetic, what does that mean? That means something has the properties of both. This energy has the properties of both electrical as well as magnetic. Radiation moves at the speed of light, which is 186,000 miles per second. Can you imagine that? 186,000 miles per second? That's phenomenal speed. Now, all of the heat received by Earth is through the process of radiation, and this is the most important heat transfer mechanism out of all of them. And at the end of this, I'll briefly describe the different heat transfer mechanisms of the atmosphere. Now, energy radiates from a body by wavelengths, which vary inversely with the temperature of that body. When I say that, what I'm getting at here is hotter bodies are going to emanate shorter wavelengths, such as the sun, because it's a very hot star, whereas colder or cooler bodies are going to emanate longer wavelengths, and this would be an example of Earth. So the sun tends to emit at shorter wavelengths because it's so hot, and the Earth tends to emit at longer wavelengths because it's cooler. Solar radiation, when we talk about the radiation received from the sun, this is defined as the total electromagnetic energy emitted by the sun. And you would think, how much of this radiation really matters, right? We don't really. The Earth intercepts just a tiny fraction of that electromagnetic energy from the sun, but it's still very intense and very important to our weather. The sun's surface, by the way, emits all kinds of different wavelengths of light. Gamma rays, X-rays, ultraviolet, visible light, infrared, heat waves, as well as those electromagnetic or EM waves. In fact, that's why it's so important for you at home to be putting on that sunscreen protection, that SPF, that a lotion on your skin in the summertime so you don't get burned. Because what that is that's ultraviolet radiation from the sun. And it's very intense and can damage your skin cells, and it can result in sunburn. If you're out in the sun long enough without that protection, the right SPF number, you can really get burnt badly. I've seen people get badly burnt, sunburned in the summer because of the intense UV radiation emitted by the sun, where it's blisters and we're talking about second degree burns, third degree burns. Yes, so you have to make sure and protect yourself because the sun does emanate that UV radiation. Now, about half of this radiation is visible light from the sun, with most of the remainder being infrared. Take a look at the bottom diagram here. I'm showing you the wavelengths in millimicrons, and you'll see the various types of energy and the different wavelengths they exist at. Radio waves on the right, for example, they propagate with longer wavelengths. Infrared rays, that infrared energy is kind of like in the middle of the spectrum. And then the visible spectrum, which most of the sun's, half of the radiation is visible light from the sun, that's where that falls, between the UV radiation on the left and the infrared radiation on the right. And then you have more intense radiation, such as X-rays, like when you go to the doctor's office. They don't want to expose you to that high-intensity radiation when you do those medical tests, because you can actually, it's not good for your body. And so they try to limit the amount of X-rays they provide. They might ask you at the doctor's office, have you had an X-ray recently, or an MRI, a CAT scan? That's intense radiation, trying to really identify internal bodily functions, for example, what's going on inside your body. And then there's also cosmic rays, which are very intense as well. We talk about solar radiation, we have to talk about an acronym known as insolation. This stands for incoming solar radiation. The IN, incoming, SOL, solar, and the ation is the radiation part. Now, insolation is the rate at which solar radiation is received by a unit horizontal surface at any point on or above the Earth's surface. And there's differences in the amounts of radiation received over various portions of Earth's surface. This is very important to the sensible weather for a specific location. The insolation received at the surface of Earth is going to depend upon what's known as the solar constant. Now, solar constant is just the rate at which solar radiation is received outside Earth's atmosphere. The distance from the sun is another factor in determining the incoming solar radiation received at the surface of the Earth. And this is very important, especially when we talk about latitudes from the equator to the polar areas. The inclination of the sun's rays, that's basically indicating how direct the sun's rays are. When the sun is overhead at solar noon, are the rays 90 degrees overhead? Are they at 45 degrees overhead? In the polar areas are going to be much lower than that. And then the amount of incoming solar radiation depleted along the journey of that electromagnetic incoming radiation from the sun. What happens to that as it moves through the atmosphere from the sun on its way on its journey down to Earth's surface? So here are some factors that can actually happen to incoming solar radiation. Okay, there's four main processes that are at play here: dispersion, scattering, reflection, and absorption. Now, dispersion occurs when the sun's rays are received at Earth's surface at varying angles of incidence, depending on the latitude. So when the sun's rays are not as perpendicular to the Earth's surface, such as the polar areas, the energy becomes dispersed or spread out over a greater area. This occurs during change of seasons in the mid-latitudes, by the way. Now, as an example of dispersion, I'm going to compare the equator versus the polar area. Okay, the sun is much more high in the sky with a greater angle of incidence. The rays are shining much more perpendicular at the equator area as compared to the polar areas. Because you might have asked yourself this question: if the sun is out for 6 months of the year, doesn't set in the polar areas, then why isn't it a lot warmer there? The dispersion aspect and the fact that the sun is much lower on the horizon is very important in this discussion. The lower the sun is above the horizon, the greater the atmosphere that solar radiation has to pass through, and dispersion then can actually work to spread out that energy over a larger area. Scattering is another process. This occurs with 25% of the incoming solar radiation. This process occurs when solar radiation is going to pass through the air, and some of the wavelengths are deflected in all directions by molecules of gases, suspended particles, and water vapor itself. Scattering is the reason why the sky is blue, why we see it as blue. So it's a very interesting topic. Reflection, another process whereby a surface turns a portion of the incident radiation back to the medium through which the radiation came. Earth reflects about 36% of the insolation, and this reflection is known as albedo. Now, the amount of reflection depends on the color of the surface, a lighter surface versus a darker surface. With a darker surface, there's more absorption of the energy and less reflection. With a lighter surface, you have more of the albedo, or higher reflectivity with a lighter colored surface. Additionally, water versus land. Land heats up much more efficiently as compared to land. Land heats up more efficiently than water. Also, a fresh pack of snow, for example, on a winter's day. If you have a fresh pack of snow, it can reflect up to 90% of the incoming solar radiation. And then finally, absorption. Earth's and its atmosphere absorb about 64% of the insolation. So land and water surfaces absorb 51% of this insolation. Ozone, carbon dioxide, water vapor directly absorb the remaining 13%. So clouds are the most important absorbers of radiation at essentially all wavelengths. So you may have noticed on a cloudy day, for example, that it tends to be cooler. A cloudy night, on the other hand, tends to be warmer. A clear day with no clouds tends to be hotter, and a clear night tends to be cooler. This all has to do with absorption. If I have a cloudy day, especially thicker clouds, the incoming solar radiation, the insolation, tends to be reflected off the tops of the clouds and resent back out to space. So a lot of the incoming solar radiation never reaches the Earth's surface, therefore we have cooler temperatures. Whereas on a clear day, those clouds don't exist, so the incoming solar radiation readily comes in, hits and heats the Earth's surface, and it's much warmer. So that's just an example right there. So if we looked at incoming solar radiation, insolation part. Now let's turn our attention to outgoing Earth radiation. So really it comes down to this. Incoming radiation from the sun versus outgoing radiation from the Earth. This occurs on a daily basis, as well as a seasonal basis, by the way. Now when incoming solar radiation, insolation, exceeds the outgoing Earth radiation, the temperature reaches its highest point of the day. So, and it's the middle of the afternoon to late afternoon, we tend to have the warmest temperatures because of this. Now, when the outgoing Earth radiation exceeds the incoming solar radiation, the temperature will reach its lowest point of the day. Now, this typically occurs around sunrise or shortly thereafter each morning. So the amount of incoming and outgoing radiation varies by the season and specific latitudes on Earth. You look at the diagram on the left, just showing you all the different things that can happen to that incoming solar radiation on the left-hand side. And then at nighttime, the Earth emits long-wave outgoing radiation to space. One thing I wanted to mention about things on the right-hand side, as the Earth is emitting the outgoing long-wave radiation, if it's a cloudy night, clouds tend to act as a blanket at nighttime, so as the outgoing long-wave radiation from the Earth's surface tries to move out into space, it tends to get trapped. So it's like putting a blanket over your skin when you're cold, right? You keep the heat retained within the blanket. Same principle in the atmosphere. On a cloudy night, it tends to be warmer than on a clear night, when all that long-wave radiation on a clear night can readily escape out into space. So, again, radiation plays a key role in what kind of temperatures we experience. Now, in the summertime, we typically have a much stronger or higher sun angle, stronger solar radiation. So therefore, in the summertime, the temperatures are hottest. And this is due to the fact that we have more insolation than outgoing long-wave Earth radiation. Whereas in the wintertime, we tend to have the sun is lower in the sky, it's not as high above the horizon, as well as the radiation is not as intense in the wintertime, like, for example, in late December around the winter solstice. So in wintertime, you tend to have outgoing long-wave Earth radiation exceeding the incoming shortwave solar radiation, resulting in colder temperatures in the wintertime. Now, if I were to look at insolation versus latitude in the seasons, this is a really cool graphic I got. Okay. Now, the different color lines represent the different latitudes. You'll see the vertical dashed lines on this graphic. For example, you see March equinox, June solstice. This is the September equinox just below that big green arrow. And then December, the winter solstice in December is on the far right, the dashed vertical line. And then on the vertical axis on the left, you have the insolation, which is measured in watts per square meter. So notice how these curves vary by latitude. So for example, in the 90 degree north area, see how much sharper that curve is between March and September when you have the sun out basically 24 hours a day for 6 months between March and September. And then that's at 90 degrees, that yellow line. And then you notice how the curve kind of flattens out, especially as you go closer to the equator. That blue line, see how flat and more horizontal that line is? For the incoming solar radiation is more constant throughout the year, right around 400 watts per square meter. So what's this getting at? Look at this graphic on the left, the Earth's annual energy balance. And notice, based on latitude here of the Earth, between 30 degrees south latitude and 30 degrees north latitude, we tend to have a surplus of incoming solar radiation. Okay? So we tend to have more heat coming in than the cooling going out between 30 degrees north and 30 degrees south latitude. Whereas we have a deficit of solar radiation, we have more outgoing long-wave radiation between 30 and 90 degrees north and 30 and 90 degrees south. So what is this telling us? This is telling us that we need processes in place to make up for this unequal heating of the tropics and at the poles. Over the tropics, again, much more incoming solar radiation, therefore you have hotter temperatures. Over the polar areas, we have a deficit of incoming solar radiation, more long-wave cooling Earth radiation at the higher latitudes, at the poles, so we have a deficit there. So a global balance must be maintained in temperature, and this is maintained by excessive heat from the equatorial region transferring or moving toward the polar areas. So bottom line here, Earth does not receive equal radiation at all points. The poles receive far less incident radiation as compared to the equator, and this uneven heating results in what's known as differential incoming solar radiation or insolation. The tropical atmosphere is constantly being supplied with all this excess heat, and the temperature of the air is higher as compared to the polar areas. And again, due to the excessive heating at the equator, heat transfer occurs from the lower latitudes toward the higher latitudes as the Earth seeks to achieve equilibrium in the temperature distribution. Additionally, we talk about heat transfer mechanisms. We already talked about the radiation and the importance of radiation in the Earth's temperature. But there's other mechanisms for heat transfer which include conduction, which is heating by direct contact. This typically occurs in a very thin layer near the Earth's surface. Convection. I mentioned this a little bit earlier in this training video. Convection is a vertical transport of heat energy. You see a lot of convection that occurs during the summer season. When you look up at the sky and you see those puffy cumulus clouds, that's an indication of convection, where the lower atmosphere and the Earth's surface is heated up and the air rises, that heat rises up in the vertical and tries to establish equilibrium in the vertical. And then you have a process known as advection. And this is a horizontal heat transfer mechanism where This typically occurs in the cooler winter season, by the way. And this is when you have storm systems in the mid-latitudes that are created with stronger pressure gradients or wind. Southerly winds tend to transport excessive heat northward towards the poles, and then the colder winds in the backside of low pressures in the northern hemisphere tend to bring down colder air from the poles to the equator. So it's a kind of a balancing act. The winds, a south wind versus a north wind, tend to redistribute the heat energy in the winter season because you have an absence of the more direct solar radiation in the winter. All right, that will wrap things up today. The training on radiation in the Earth seasons. Hope you enjoyed video 1 of the summer weather training series here at Spot On Weather. Here's where to find us on social media: Facebook, Instagram, Twitter, and our website. You go to spotonweatherweebly.com. You can get a lot on that website. Believe me, I've been working on it for years, including weather photo galleries, some cool cloud pictures in there. You can go and look at our 7-day outlook, our latest forecast. You can go and look at occasional blogs that we throw on the website. You can get a look at archives, weather archives, big weather events, weather links if you're doing any kind of research, all on the spotonweatherweebly.com website. Check it out. I do a lot of my posting on Facebook for the forecast and the weather updates, as well as Twitter. Those are my 2 primary social platforms. Feel free to subscribe to Spot On Weather for the most accurate weather forecast. And also YouTube. We run the YouTube channel here. We really hope you enjoy the learning about the weather, and we love sharing it with you at home. We're very passionate about it. So that wraps things up today on the radiation and the seasons. Hope you learned something, and I wish everybody a great day today. Take care.